Start. It's going to be a relatively, hopefully interactive, relatively simple talk about kind of the calculus of size distributions and simple things. So, anybody can tell me something about processes and parameters that can be inferred from size. Why do we care about size? What scattering is affected by size? But not just optics, just big world. What processes and what? Nutrient optics. How is nutrient optic affected by size? So it's surface to volume. These are things that surface to volume, does it decrease or increase with size? Who has more surface? What? The bigger you are, the less surface to volume you have, and therefore you're less, you can let, processes that are surface like nutrients or getting rid of waste product are harder to do for larger organism than it is for a small organism. What other processes? Sinking rate. How does sinking rate relate to size? Increase, and do you know how? Stokes' law. Anybody remember how it's dependent on size for small organism? It goes like diameter square. So if you have twice the diameter, you're sinking 4 times as fast for the same density. So, carbon flux, all these things, they're size dependent. Anything else you can think about? Prey predator. Does it matter if you're bigger than your prey or not? Sometimes it does. So, okay, so this is kind of why we care about size. I mean, obviously, as we said throughout, it's affected. Yes? Yes, you can. It has to be about size, though.
About the sinking, right?
Yes.
The inorganic and the organic, they will sink differently.
So let's think about it. It is relevant. What's the difference between an organic particle, it depends what, but let's say phytoplankton as an organic particle, or bacteria. What is it mostly made of? What are we mostly made of? Water. We're mostly water. And so the density difference with the water next to it, the water that's better, is relatively small compared to something that's solid on the inside, like a quartz particle, like a dust particle. But the settling goes like the density of the particle minus the density of the water. But it goes like diameter squared. So yes, this is important, but it goes linearly with your difference in density from the water. But it goes non-linearly with size. Good question. So now I'm gonna talk to you a little bit about how we do size distributions. So I'm gonna turn this off. Yes.
Can you a little bit more about the constructs in size distribution?
Well, so I mean, there's if same material is packaged, same material, so no change in density, is packaged to bigger particle, it's going to fall faster. Now there is a twist to it. Aggregates are these loose agglomeration marine snow, where most of it is made of water, actually 99.9 water. But on at least the literature, the seem to be the consensus in the literature that the aggregates fall faster than their component particles. So it's a way to get stuff to depth. Now, fecal pellets are dense aggregates, which is different than marine snow. And one way people characterize that is with fractal dimension. And one way to think about the fractal dimension is how much see-through is this aggregate. Can I see through it? If I can see through it, its fractal dimension is less than 2. If it's totally solid, there's no empty spaces in it, it's 3. And there's ways to calculate it, and it relates directly to the amount of water in it. We can do a whole different lecture on calculus of fractals for aggregates, and I can send you to the literature about that. Okay, so now we're sizing particles. We're getting a bunch of particles, and we're sending them into different bins depending on size. So, this is going to be D1, all the particles that are from D1 to D2. This is going to be, and D is diameter here, D3. D4, here it's going to be Dn minus 1 and Dn. Okay? How many bins do I have? So we're going to have n n1 of particle between D2 and D1. Going to have n2 particle between D3 and D2. What's going to be the last bin here? So 5, and I have Dn minus 1 Dn. We're going, so which one is this going to be? N minus 1 or N? N minus 1. So I have one less. This is going to be Dn, Dn, N minus 1, or N minus 1. This is N. Yeah. Okay? So these are all the particles that I have in my size distribution. Now, do you think it matters where I put the boundaries? If I move this boundary sideways, would I get more particles? Per beam, yes. So now let's start by doing a histogram. So with this data, I can do numbers per volume that I filtered. So it's going to be a number per volume. And Mike, if you can adjust the camera as we go, just so people, and then I'm going to just put the numbers. So here it might be high, here it might be low. So I'm basically just doing 1, 2, 3, 4. I have 6 bins there. Okay, and this is, so this is going to be my diameter, and this is going to be my N of D. How many particles did I have in each bin? So again, here I'll have D1, D2, D3, Dn, N minus 1, Dn. And I have my N minus 1 bins. Okay, all clear. But we said one of the problems I have with this representation that it's bin dependent. Now, so how do you think we can get rid of that bin dependence? What can we do to make it bin independent? Because really we want a size distribution that does not depend on our instrument. I want to be able to compare a Coulter counter with a list. They each have different bins, but so how do you go about making it bin independent? What? Here, decrease the size of the bin, but then you might have one particle here and no particle here, 2 particle here. You might get into counting issues. You're going in the right direction, but you don't change the bins. You can't change the instrument. You buy the instrument. It does this to you. But how do I get something that is independent of the bin size of the instrument, that represents size? Get a function to fit this? Anybody has another idea?
Can you just normalize the histogram by the bin size?
Exactly. So what you do is the following trick. You say, rather than look at ND in number per volume, I'm going to divide it also by the size of my bin, delta D. So now I'm going to do a new size distribution. And I'm going to denote it differently. So if this one was D of N, N of D, big N of D, I'm going to do one that's going to be little n of D. And little n of D is basically equal to N of D divided by delta D for each beam. So now, instead of, this is going to be equal to, for my first beam, it's going to be N1 divided by D2 minus D1. And then it's going to be n2 divided by d3 minus d2, n minus 1 divided by dn minus dn minus 1. What units do I have now for that size distribution? Anybody has an idea? This one was number per volume. Very, very simple to understand. But now what are the units here? Number per volume per size. Per meter, per micron, per centimeter, per anything that is representative of the units of this. So when in our world, it's usually per micron. It doesn't have to be. So you add, so now you're going to have units of number of particle I measured, per milliliter of water that I filtered, that I analyzed in my culture, per micron. So now I'm adding here a per micron. And how does it look? Well, for this one, just let's say this, it's going to be this point. And for this one, it's going to be this point. And for this one, it might be here, here, here. It represents the bin, so I have a point. It represents the whole bin. I can do it also with a bin. Now the question is, where do I put that point in order to do, what's the diameter? Since I average now everything between this and this, what's the diameter that goes with this? Which diameter do I assign to here? So here I had, a bin, which is wide. Now I want to say what size it represents. What are these numbers, what size they represent? Do they represent, obviously they're all the particle between D3 and D2 for this one. But I have to, if I want to graph it, if I want to feed a function to it, I need to know what D do I give it.
Mean of the two diameters?
You can do a mean of the two diameter. You can say, okay, the D I'm going to use now, it's going to be little d. Little d2 is going to be d3 plus d2 divided by 2. So that's just in the middle, one way. Some people, so do you have a sense in nature how particles are distributed? Do we have many more small particles than big particles? Kinda. So some people say a better representation of the average size of a bean is actually the geometric mean. It's going to be this D2 times D3. So for the list, for example, this is how the bin size is calculated. The size that goes with the bin. You can get the boundaries of the bins as well. But this is how it assigns when you're plotting in a graph and you want to plot number concentrations as a function of size, you have to choose one of those, and it uses the geometric mean. Which one is bigger? Always. Bigger or equal, but it's really bigger. Yes?
I'm not sure about that. D2 equals square root of the difference?
No, it's not a difference, it's multiplication.
Oh, okay.
That's the geometric mean.
Okay.
It's something you learn in algebra. There's one that's always bigger than the other. Right? This one is always bigger than this one. Do you want me to prove it to you? What? No. I mean it's algebra. It's not related to size. But this one is always bigger than this one. Do you want me to show you?
And those are the points at which the ends of your bin.
No, these are the end of the bean.
Right.
This is going to be a point that you choose to assign the concentration to your bean. So how do we do it? It's relatively simple to prove it. So I have, I'll call it, say, just a different character than what I'm using now. Well, okay. Let's do it like this. I'm gonna square this one. What do I get? 1/4 times d3 squared plus 2 d2 d3 plus d2 squared. Nothing to it. Okay? Now I'm going to square this one. This is equal. So this is this squared equal this. Now I'm squaring this one. I simply get d2 d3. Okay? Now I do the difference between the two. I do the difference between these two. So I have here the 2d. I'm differencing, so I'm going to get 1/4. So this is going to be the square of this minus the square of this d. Okay, you're going to get, I'll put it in, minus 2 d2 d3, because I multiplied by 4, put it in, I had a plus, minus, plus d2 squared. And why is this always positive? Because this is simply d3 minus d2 squared. This is 1/4 d3 minus d2 squared. And since my d3 is bigger than d2, it's always positive. This is bigger than 0. So this is how I know that this one is always bigger than this one. Said it's algebra, it has nothing to do. Okay, so we got to this. So there's one major issue we did not talk about. What's the size of this?
Depends what you define as size.
Well, tell me.
It's width.
It's width. So there's actually, I mean, at least 3 different sizes associated with this object. But we want only one size. So what do we do? Use volume. So I calculate the volume of this, and how do I translate it to size? Well, we get to surface in a second. So I know it's volume. How do I get size out of the volume? So an equivalent, equivalent spherical. So I have a excellent. So I'm taking my non-spherical diatom chain. I have my diatom chain, or my Ketosaurus. It's going like this. And I'm saying, okay, I'm going to transform you into a sphere that has the same volume. I'm going to measure its diameter. And this is what I'm going to call my diameter. So this is an equivalent sphere of the same volume. Adao just said, well, it doesn't have to be volume. Maybe surface area is more relevant.
Well, what I meant was you can take the volume and divide by the surface.
Excellent. So that's something else you can do. So Adao said, I don't have to even go to a sphere. I can measure a size that's related to this particle, where I do my d is its volume divided by its surface area. It has the right units. It's going to give me a diameter. If I did it for a sphere, how will it relate to the diameter? If I did it for a sphere, this is going to be 4/3 pi r cubed divided by surface area would be 4 pi r. So this is going to be equal. So this is for a sphere. I'm now doing a sphere. No, what am I saying? Pi r squared, 4 pi r squared. This is the cross section. Sorry. Absolutely right. So I'm getting, so this is going to end up being, and this is cubed, this is going to be r/3, or diameter over 6. Which is okay, as long as you know what it is. Or you might maybe do 6 times that, just so it agrees with the diameter for a sphere. So this is one way. Some people use an equivalent sphere that has, so this is same volume. You can use one that has the same surface area. or same cross-sectional area. You just have to be aware. So it's not enough to put diameter when you do a size distribution. It will be really good if you write diameter of an equivalent volume sphere, of diameter derived from volume divided by surface area, or cross-sectional area, or so you have a sense as to what is happening. And it turns out different methods are sensitive to different properties of the particles. So if you think of a Coulter counter senses particle based on their impedance, the change in resistance, electrical resistance, in the volume in which the particle passes. So, they're passing one by one really fast. So the bigger the volume of a particle that's non-conducting in a fluid that's conducting, the more impedance, and so you get something that's proportional to the volume. So its diameter is the equivalent sphere of the same volume. What about when you take pictures with something like the IFCB? What do you see with a camera? What?
The surface.
A cross-section. Not even the surface, you see a cross-section. In some instrument, it aligns the cross-section so you see the biggest one. In some, it's random. Just see whatever cross-section passes. Yes, Colin?
And I think it's important when you're trying to relate the size indices to some optical property or some geochemical property to think about what's important there. Because we're talking about biomass. Biomass scales like volume, but maybe absorption squares like cross-section. And so, you have different geometric sensitivities to your measurements, the desired quantities that you're looking at.
And same happens with optics. We'll do it next week when we do meat theory. But when you're a tiny particle, much smaller than the wavelength, the optics is the scattering and the absorption are sensitive to your volume. When you're much larger than the wavelength, this is called geometric optic limit. It's shadow. It's your cross-section that the optics is sensitive to most. So depending on the regime, even in optics, you're getting different, and in between, it's a mess. So just things to remember. Now, okay, so we understood. So still, why is it then, given that all these methods are so different, what are saving grace? Let's think about phytoplankton. What range of sizes do they have? How many orders? So let's think about. So I'm starting, say, at a Prochlorococcus. What size is a Prochlorococcus?
Less than 2 microns.
Much less.
Prochlorococcus,
Yeah.
0.7.
0.7 micron. Let's say. This is diameter. And then the Noctiluca that you were working on. How big are they? Yeah, your Noctiluca. Up to 1 millimeter. So I'm having more than 3 orders of magnitude, and then we have chains of diatoms that can be. So let's say this is 1, this is 10, this is 100 micron, and this is 1,000, which is 1 millimeter. So yes, we have things that have ratios of 1 to 10 in shape, but still, once you put them on a much larger scale, to order 1, what matters, you can still use size distribution that are an equivalent spheres, as long as you understand the biases and the uncertainties that go with it. But it's still a concept that's very useful, even though we rarely see a sphere in nature. Okay? So this is why we can still somewhat get away with it. Is because we're spanning so many sizes. This is just phytoplankton. I didn't talk about bacteria and viruses and everything that's on this side, and the zooplankton and everything else that's on this side. And sediments. So clays are going to be here, the single clay plates, and then you're going to get silt and sand and everything else, and pebbles going this way. So again, all the relevant. This is why we can get away, even though clays don't look spheres, they're plates, they're tiny plates. So I have my size distribution, my differential size distribution, the one that's easy to work, and hopefully all the instrument will fall on top of each other no matter what bean size they have when we do that. So I have my, and let's make it somewhat realistic. So this is D. This is my small n of D, it's my differential one. And now I have my, and we can even do it on a log-log plot. And the question now is, and let's say this we'll put of a sphere, of an equivalent sphere here, same volume. And the question now is, how do I change that into a biomass? I have numbers. But what I care about is how much mass there is in each bean or in each size. So this is my functional, I can feed a curve to it. People do that. But how do I move from numbers into something that I can put in my geochemical model? What do you think? How do you move from number to volume? If I know how many things I have here, how do I get a volume? A total volume in this bin. What do I have to do? You know it, guys, come on. Do you know the volume of one particle in that bin? Before we get to, let's do volume before we do biomass. Let's say biomass is volume times density. I'm not sure about density, but volume I can do. So how do I move from here to a volume? It's not difficult. Come on, guys. Julia, you know it. Let's say that here I have 6 × 10⁻³ particles per ml per micron. What do I need to do to now get a volume per ml per micron? Volume of stuff in that bin. See, I have here 6,000 particles per ml per micron. That's this point here. Now I want to know how much volume does it represent. What do I do?
Do you know what D is?
I know what D is because this is my D1. I assume it's a sphere again, and all I have to do is just multiply by 4/3 pi diameter over 2 cubed. I mean, I know what it is. It's actually 6 diameter cubed, 1/6. But I always remember it from my childhood for a radius. So all I do is multiply by the volume associated with this size. And since we're working with equivalent spheres, because that's the only, so there's something very special about spheres. It's the only object that can be described with one size. It's also an extreme object. I mean, people think about it as a good average. It's not a good average because it has the least surface area to volume ratio of any convex shape. So either you're elongated or you're squat, you always have more surface area to volume than a sphere. Just so you remember. Sphere is an extreme shape. It's not a good average shape. But it's the one shape that has a single size to describe it. And since we're using a single size to describe our size distribution, now we can do a volume distribution. Now, what do you think is going to happen as you multiply a curve like this by diameter cube to get a volume distribution? Will it get steeper? Will it go like in this direction? Or will it go in this direction? I'm multiplying by diameter cubed. So when the diameters are small, I'm multiplying by a small number. Diameters are large, I'm multiplying by a large number. So it's going to go this direction or this direction? This. Is this clear to everybody? So volume distribution are much shallower than area distribution, than number distributions. Okay? And we know how to go from one to the other. If you have a volume distribution, divide by the volume, you get the numbers. If If you have numbers, you multiply by the volumes, you get a volume. And once you have volume and say you want biomass because your model is in carbon, then you go and open papers like Menden do or God knows what, and you convert volume of organic material between this side and this side to biomass with a fudge factor, assuming that you know something about the uncertainties. All clear? Yes, Colin.
And just note that when we were doing the list, we were looking at the size distribution of particles in the software. It was a volume distribution, so it was the latter that was presented. It had already assumed some shape.
And it's even worse than that. It was a volume distribution in part per million. So part per billion in volume of material to volume of water. So you can see how that can be in part per million. Microliter per liter. So microliter of stuff in a liter of water. That would be a part per million. But it was not divided by the size bin. The way it reports it is without the division by the size bin. So it's a number distribution, the big ends. It's this distribution without the division by the size of the bin. So to get that size distribution, you have to know the bin boundaries, and you have to divide by the size of the bin, that volume distribution, to get the differential volume distribution to which that's independent of the bin size. Otherwise, if you don't divide by the bin size, you always have a size distribution that's your instrument specific because it's bin dependent. You cannot compare it to something else. Is it clear? Any questions?
If you're measuring clay, is there something you could do that you have spheres for an assumption?
No. Not that I can think of. So actually, brings something else. We use filters to also help us bin things into sizes. You know, you put a 0.2 micron filter, and then you're measuring optics of that, and you say, oh, this is the fraction bigger than 0.2 filter, the 0.2 micron, and then you put a 1 micron. Or if you're a geologist, you have sieves of different sizes, those of you have seen, and you put them on a shaking table, and stuff falls down sequentially. The big stuff is captured here, smaller and smaller. But all of those have what we might call a pore size or a sieve size. So if the geologist one is the easiest to think about. So I have something like this. It's a mesh made of metal for the large fractions. What goes through it?
Everything's smaller than that side.
Everything smaller than this side. But what about something like this? How about my chalk? It can go through it if it comes in the right orientation. You know, you shake it until here I go. So there is no perfect filter. There is no perfect filter in the world because things are not sphere. If they were sphere, you're totally right. No sphere that's bigger could go through. But what it means is that each filter is a pass, if you will. This is diameter. It has a certain efficiency. And let's say it captures with 100% efficiency everything that's bigger than this. And then there's some finite probability, and then these guys go through. And maybe some of them get stuck on the filter. So this is actually maybe not even true. It might be that you're ending like this, because everything smaller can get absorbed to your filter, let's say. Okay, so this might be the nominal pore side. This might be what they'll call a nominal pore size. But it's never perfect.
And so now superimpose the size distribution on top of that, because your x-axis is size, right? So if you superimpose the size distribution, it's messy. And you know, you can get that curve from manufacturers. It's horrifying.
But it also depends on the particle that they tested it against.
They usually test it on beads, but
So beads are spheres.
right.
So that's best case scenario. Okay, so really important. Keep this in your mind all the time when you deal with size distribution. Where are the uncertainties? What might cause it? Why do I get? I take a sample for POC. Okay, and so I take my filter, and I filtered seawater, and I run the filtered seawater through, and I send it to get analyzed, and I get a non-zero POC. But it was all dissolved stuff, 0.2 micron, and I'm putting it on 0.8. Because the stuff gets adsorbed to the filter. The organic material that's in the dissolved fraction adsorbed to the filter, and now it's counting as POC.
Or you just have a broad efficiency, and it's an actual submicron particle that's captured.
Because it's this big, molecule that has a thing that gets hung to the filter, and okay, really important. So also, when you think about a blank, you have to think about it. It's not enough just running just a salt water, or water blank. You also want to know, is there a blank because the so-called dissolved material will count as particulate. It's all issues that you learn through. I'm just trying to make shortcuts for you so you don't realize them when it's too late. Okay, we go back to this, and I'm almost done. Questions? Comments? And again, despite all these problems, we can do great science. We just have to because the signals are big, the orders of magnitude are big, but we just have to be aware of the limitations of all these methods. So we say in general, physical measurement associated with waves, like sound. We use sound and we use light to sense particles. And I talked to you about it before, but each instrument we use has certain sizes it's most sensitive to. And that's where you get the most bang for the buck. So if you want to do a large size distribution, you have to use many, many sizers that use different principles to give you a size distribution. With images, with your camera as example, you cannot resolve anything that's smaller than a pixel. You have a physical limit to the size of a particle that you can resolve. But there's another issue with that, is that I can have a sub-pixel particle, a very bright one, and I'm going to count it as a whole pixel. It's below, and suddenly I have, if you will, particle I'm not supposed to count affecting my counting. And also, if they sit right in between these four, if they're bright enough, I'm going to get 4 pixels. So one way this is dealt with is that because there's so many small particles, we're going to put a threshold. We're putting, in imaging system, we put a threshold. If the signal is less than X, it's not counted. And people tune those thresholds because if you're too sensitive, you get a lot of noise. All of these are going to light up because they're small particle, but they do scatter light. They are in homogeneity. But if my threshold is too high, a transparent particle that might be relatively large, but it's kind of transparent, loose, I'm not going to see it because it's just very transparent, it's very see-through. Jellyfish, something like this that I might be interested in, but it looks so much like water. If I set my threshold too high, not going to see it at all. So every imaging system has those knobs, and people play with those knobs to get an optimal, what they'd consider an optimal detection. So be aware, there is no objective way. I mean, there's probably, you can do an objective procedure that you can describe in a peer review publication as to how you decided to set the threshold. And you have to report it. It'd be good if you report it because this is how people will learn. So this is a classic paper on size distribution in the ocean. It's a paper where they used really only a Coulter counter themselves, but then went to the literature and looked at what's out there. And what they found, this is in part per million, again, particle concentration, and the phytoplankton is based on Coulter measurements. Everything else is, as I told in literature, that relatively speaking, this is a linear scale here. You get the same amount of biomass per log beans. So if I go, my beans are 1 to 2 micron, 2 to 4 micron, 4 to 8, and I always double them or whatever other power law, you get similar biomass in logarithmic size bins, going from phytoplankton to whales. And then you can discuss what are the ecological, underpinning of this. What's the efficiency that passes stuff from one to the other, etc. But just in terms of size distribution, this is kind of, and it turns out this is associated, this kind of size distribution, with what we call in the field a Younger size distribution, which is a power law size distribution, which when it's differential with a -4 slope. And that's consistent with this Sheldon picture. Yes?
But that's with the number distribution normalized to the bin size?
Yes, it is. So it's -3 if you don't normalize, and therefore when you multiply by the volume, you're going to get them to be on a line. Pretty much on a similar line. And then there's this paper that I like a lot too. It's a paper, I didn't write it on, it's in your box. It's by Jackson, 1997. The only paper I know that tried to build a size distribution going from 10 to the -4 centimeters to 1 centimeter. So they have here 1, 2, 3, 4 orders of magnitude. And I think they use 5 different instruments to do it. Measurement in Monterey. In this area of the curve, they used impedance. They had 2 Coulter-like instruments that use impedance for measurement. All the big ones, they use imaging. And they're able to merge them into one size distribution. That look, again, on a log-log, everything look like it's a power law size distribution. When they do the volume distribution, this is when you start seeing structure. It's not, you see the difference. By eye, you fool yourself to think, oh, power law fit perfect. Look how well my power law line, this dashed line, fits. This is from 10 meter, 50, and 30 meters. But once you do the volume, suddenly you can see features that are really important. It might be a bloom of a certain phytoplankton, it might be a resuspension of large sediment, it might be aggregation. But this is the same data, just here in volume and here in numbers. And they do some treatment for fractal dimension that you have to go in the paper to do, but it's just making sure they count material and not the water and interstitial water. So highly recommended. Now what they find is that each system to do size has problems. We just talked about the problem in the small sizes. So there's detection, there's thresholding, things like this you have to do. What about the high size? What's the problem, say, of a lift that supposedly give you 250 micron particle size? What's its problem with 250 micron particles, do you think? Again, assuming we have a size distribution that's like this. I have a size distribution that goes like this, with a d to the -4. Or if let's do this, nd. And this is a log-log plot, so it looks, this is log of d, and this is log of n. This is log nd. What do you think is a problem in the larger bins? They're rare. It's really hard to count particles that when you have a tiny volume, you're optimizing for somewhat the concentration, say, in the middle of it. The big ones are really rare. So if you want to do fish, what size ocean do you need to get good statistics? How much ocean do you have to filter with a net? A lot. If you phytoplankton, you have 10 to the 6 per ml in 10 to the 4th, sorry, per ml. Bacteria 10 to the 6 per ml. Kind of back of the envelope number. Zooplankton maybe 10 to the 2, the tiny one per ml. The krill maybe 1 per ml. So you have to match your volume to what you want to count, just like when they count people for a census. to get reliable statistics. You're not going to ask two people for their opinion and tell us who the president's going to be, because it's not enough to get representative statistics. So you have to get a lot, and which means you have to cover a lot of area to get. So there's a great paper by Dave Siegel, I didn't put it on, I should have, in '98, which discusses this point of when can you start treating a population as a continuum, as opposed to independent individual in your sample. And you can start doing it if you have in the volume that you're analyzing at least 400 individuals. That's where you can start treating them as a continuum, as something, because then your uncertainties go down to less than 10% in counting and things like that. So you want whatever bins you use to have at least 400. It's very rare that people get to 400 in the large bins, I can tell you that. So one way to do it is you actually count, you aggregate size distribution until you have sufficient so you can get the statistics. There's all kind of ways to do it, but just things to remember.
400 what?
400 individual per bin to get reliable statistics for that bin size. So that's going back to this guy. Here, you want to have at least 400. So if you work with culture, you want to look at the bins that have order 100 or more particles. If you have 20 particles in the bin, your uncertainties are really large in your counting of that size fraction. That's in this, so when you're doing it within the bin. So when I do this number per volume, in my bin, I want to have at least several hundreds to have reliable statistics in counting. So this is why on the large end, any imaging system or any other system, sizing system, is not very reliable. And on the small, we said it's all the thresholding that you have to do. Even for an impedance, a Coulter counter, you have to, if it responds to every particle that goes through, it will be really noisy and invent a lot of small particles. They have to put a threshold. So any imaging system you'll ever use has problem in the big, problem in the small. Be aware.
I know when you scale it up to per cubic meter, your one particle in your big bin suddenly becomes really important when the error bars are massive.
So as I said before, we do the measurements and then we fit curves to them. I'm just going to show you a few curves that you might see repeatedly in the optical literature. So the simplest one is the one I just told you about. It's one that's a power law size distribution. Somehow early in the literature, we used to call it hyperbolic. There's nothing hyperbolic about this function. It's a power law function, but me and others called it hyperbolic. And we stood corrected by Kurt and have never used that name again.
Yeah. And it's technically, it's only a Junge distribution.
If this is 4,
Minus 4 slope.
then it's a Junge.
You can say it's a Junge-like or hyperbolic, but none of those names is really correct. Junge was an atmospheric guy, and he only did the minus 4 slope because that's what worked for the atmosphere.
And the other thing that's interesting with this kind of size distribution, it's what you'll get if you took a bottle and broke it on the floor. Or things like this. It's tend to pop out naturally. But if you show this size distribution in an ocean optic meeting, one of our members will undoubtedly stand up and say, "This never applies anywhere." And that's Robert Staven. I'm just preparing you not to be. It sticks this point in him that immediately he gets all. So for him, there's another one. This is called the gamma distribution. This is from a paper by Risevich, which I put on your, and basically it's very good in fitting many things. It can fit something that looks like log normal, but it can also fit something that looks like a power law. This is from Wikipedia. So depending on the parameter you use, you can fit many different kind of believable function you'll see in the field. So this one is a 2-parameter function. The reason we like this one is it's supposedly a 1-parameter function. It's not totally, because what dmin and dmax you use will affect what you get. So, but that's true in all of them. What boundaries you use would affect your fit, as we said for CDOM and other things. So this is a 2-parameter distribution. And the one that Risovich is very famous for is actually has a sum of 2 gamma distributions. And here is an example of him fitting it to, this is number per centimeter cube. So this is for the differential one. And that is function of micrometer for data from 20 meters, 0, 1,000 meter, 100 meter. And it seems to fit pretty well. And it allows him to have some kinks in it by having these 2, one for big particle, one for small particles. So you'll see that it's called the Risovich size distribution. It's doubled, so you have 1, 2, I guess maybe 3. And so you have the large, 3 in each. Plus the numbers. Yeah, so 8 total it looks like. But he gives the values that he found to fit the best in the environment. So something to start with. If you do not want to fit, but you want something to see that, so he gives a range of, the range is limited in his data set, and he provides that range. But it allows you to have a kind of a bimodal volume distribution. It looks like this in a number distribution, which in coastal areas. So to summarize,
Can I ask a question?
yes.
So when you get your PSD data, do you just kind of like have a bigger one and always use it, or do you look at the distribution and then pick one of those? Or
So I'm a fan of nonparametric statistics, which means I tend to look at things like what's my median size, because these tend to be robust. What's the distribution around the median? So what's my, things like that. It depends on the application. I mean, so if I try to use, see an inversion from optics and how it relates to size, I will usually compare it to a median size. But yeah, of the underlying particular populations. But it really depends on what you're after. Or I could fit a curve because it's easy, and then see how the parameter of that curve changes as I get close to the bottom for a suspension compared to higher up in the water column. It all depends on what you're trying to describe with that. So again, size matter, but it's important when you ever do size distribution to say what kind of size do you mean. Is it equivalent sphere? Is it equivalent sphere with a similar cross section? What are you trying? Everything looks great on a log-log plot. It hides a lot of details. So it's really worthwhile to also plot volume distribution. It's where you're going to see suddenly the population of phytoplankton that are blooming or others that will pop up. Much harder to see on that number distribution. So the calculus is not tremendously hard. Once you get into it, it's quite simple, but the details are important. So watch for units. When you compare to other paper, did they do it per bin or not per bin? All these things will help you a lot. Simple models are useful, but again, like any simple fit, you want to make sure that you test it, you see that it's consistent. And another thing, so beware of handling is something to remind myself. When you take a water sample from the environment and then run it through filters, you're changing the size distribution. When you run it through the spigot of a Niskin bottle, you're changing the size distribution. So be aware of it. Doesn't mean it's bad, but be aware that you're going to affect the size distribution of whatever it is you're measuring. Because in the field, there's also a lot of loose aggregates, loose particles that and they're very hard to measure in the field, because even if you have something like the list, it generates turbulence around it that can break particles. So what you want as much as possible is non-invasive methods, but it's hard to do, particularly for the small guys. So just remember that the particle you will tend to have steeper distribution in lab than you'll have in the field, because you're passing mass from large, loose particle to smaller, more solid particles. So it's a property that's affected by us as we handle particles. Yes?
Well, the other you should have filter them, and then you see how that affects your final, which is basically controlling for the effect of your instrument.
So we with Paul Hill, who's going to be here next week, this is exactly what his lab does. So they have cameras in the field looking at sediment, aggregated, going through the camera, and then they take samples and they specifically disaggregate them and run them through a Coulter counter. And they report this as the disaggregated size distribution. So they have what they see in the field and they have the disaggregated. So you can do that if you have the systems to both measure things in the field as well as measure them in the lab. Exactly that. But the thing is, you want to know the degree of handling. So what they do is rather extreme. They make sure they disaggregate. They disaggregate them so that they measure the component particles as well as the aggregated particles in the field from the same depth and time. So that's one way to try and control, to give you a sense of how much aggregated the population is. One thing we did here off the dock one year is we had two lists, one that we ran the particle through an impeller pump, the CTD pump, and one that didn't, and the chamber. So one had the chamber and the impeller pump on the intake, the other was open. And we saw really nicely how much aggregated the particles here are by passing from one to another. Yes?
Would you expect to see more smaller particles if you could hold everything else constant, but just let biological activity keep ticking?
I mean, you can see both ways. I mean, prey-predator interaction could go both directions. You can make big particles, and you can. And a virus, which is a tiny particle, can kill the big guys, and then you have a lot of the small guys. I mean, it goes all directions. There's many processes that can flux stuff from one or.
But by looking at the change in the size distribution, you might be able to infer what those processes are.
I mean, this is really, really important what Colin just said, is that if you monitor size distribution, you can learn a lot about the dynamics. Okay? We're all done? With me?
Yeah.
Sorry.
Colin, make me show this to
No, you brought it to my attention.
but you told me I had to show it. Now, seriously, this is a good example